happy to come here in a face-to-face, and I would like to thank Sofian organized this fantastic meeting in Cambridge. My topic today is about comparison of ion channel TRPA1 and PIEZO1 among species. So this is an outline of my talk today. In the first part, I will show you the data of TRPA1 between human and chicken. And in the second part, I will show you the data of PIEZO1 channel between human and chicken mainly. It is very important to find critical amino acid for regulation of ion channel in human. We know that SNP database is quite useful to find such residues. However, it takes some time to test each SNP. And of course, you know, such kind of trials are often not successful. So our strategy is quite simple. Just compare ion channel between human and other species. Here I show you a phylogenetic tree of TRPA1 and piezo. So as a counterpart of human, we chose chicken because they are genetically, it's not so far each other, it's not so close. So that is why we choose chicken. So because you are expert about ion channel, I skip introduction of TRPs and piezo. I'm sorry, I just show you original data. So here I showed you the response of TRPA1 to external zinc. External zinc is potential endogenous agonist of TRPA1. As Professor Pataputin's group reported, it is certain that application of external zinc to TRPA1 in human and mouse induced very good response. However, in chicken, as you can see, application of external zinc did not activate any current. While AITC is an agonist of TRPA1 induced very good current, suggesting that chicken TRPA1 is unique about sensitivity to external zinc. So to confirm further the difference of sensitivity of zinc between human and chicken, we measured direct elevation of zinc to use fluorescein-3. As you can see, when we applied zinc externally, clear zinc response was observed in human TRPA1, but not chicken, suggesting that chicken TRPA1 is again quite unique against that external zinc. In the lower panel, I show you the response of TRPA1 against AITC, electrophilic compound activator of TRPA1. As you can see, AITC clearly induced clear inward current at minus 90 millivolt, suggesting that AITC response are quite similar between human TRPA1 and chicken TRPA1. Again, zinc response is much different between human and chicken. So we have two possibilities to explain the difference of TRPA1 against zinc in human and chicken. First, chicken TRPA1 is intrinsically insensitive to internal zinc, or chicken TRPA1 has lower permeability of zinc. To test such possibility, here I made a mutant in which aspartate residue of 915 of human was mutated to alanine here. So when we applied zinc to this mutant, zinc response disappeared, while AITC induced very good response. So this means that zinc permeation of human TRPA1 is quite important for response by zinc in human. So to further confirm the importance of permeability of zinc through TRPA1, we applied zinc to this mutant and to chicken TRPA1 in the presence of zinc ionophore. So as you can see, zinc itself did not cause any response. However, in the presence of zinc ionophore, clear response was observed, suggesting that chicken TRPA1 is intrinsically sensitive to internal zinc, but permeability of zinc through chicken TRPA1 is quite low compared to the human TRPA1. So next step is to find the mechanisms involved in the lower permeation of zinc through chicken TRPA1. Here we made a triple mutant in which 3 amino acid residues are replaced. Because these amino acids are reported that quite important for the calcium dependency of heat-evoked TRPA1. As you can see, these 3 amino acids are replaced in human, shown here. So we consider that these 3 replacements are quite important for zinc permeation in human. However, even though we made this mutant, application of zinc induced a quite good response, suggesting that these 3 amino acids are not involved for lower zinc permeation in chicken. Meanwhile, we noticed that this amino acid is replaced between human and chicken, shown here. So in human, asparagine conserved, but in chicken, this allergen is mutated to histidine. So we considered that this histidine replacement is quite important for regulation of zinc in human. So we made this mutation where arginine at 919 of human TRPA1 was mutated into histidine. As you can see, even though we applied a very high concentration of zinc, did not cause any kind of response, suggesting that this arginine and histidine residues are quite important for regulation of zinc permeation in TRPA1 between human and chicken. Unfortunately, this mutation is not reported as a SNP. So we therefore I'm sorry. So conversely here I changed that. I changed this histidine to arginine in chicken TRPA1, vice versa. Unfortunately, even though I applied that zinc at 30 micromole, did not cause any kind of response, suggesting that this replacement is important, but not so determinant of the low permeation of zinc in chicken TRPA1. Nevertheless, we have noticed that arginine 919 of human TRPA1 is quite important for regulation of zinc permeation in human TRPA1. So we explored SNP database, and we found that 3 SNPs which produce mutants are identified. So this is our first SNP, SNP1, which produce truncated TRPA1. Of course, this is dysfunctional. Even though we applied zinc and AITC, we cannot get any kind of response shown here. Second SNP, in which arginine is mutated to glutamine, had a very similar response to wild type. So in this SNP, property of TRPA1 channel quite similar to wild type. So this is a third type SNP in which arginine is mutated to proline. In this case, when we applied zinc to this mutant, we cannot get any kind of response, while AITC induced a very good response, suggesting that this mutant caused by SNP3 is like a loss of function mutant of TRPA1 in human. So we actually applied a similar strategy to PIEZO1. So first, I will show you the human PIEZO1 currents in several types of human cells. Here, I showed you that current in human brain endothelial cell, human aorta endothelial cell, and human osteoblast cells. Here we applied pressure to excised outside patch, induced clear inward current at minus 60 millivolt, and these currents are clearly potentiated by application of Yoda. So in particular, the current potentiation at 20 millimeter Hg shown by red, this is very clear. So application of pressure induce PIEZO1-like current in human cells. So here I showed you the response which recorded in outside that patch. When we apply 20 millimeter Hg pressure, you can get a very clear single channel-like current, and this current, channel current, is clearly potentiated by Yoda. So channel property is compared between pressure-induced and Yoda-1 induced. So channel property quite similar. And also this channel current is recorded in human aortic endothelial cell, and this channel property is quite similar in PIEZO1 heterologously expressed in hex cell. So here I showed you that pressure-induced PIEZO1-like current in human knee joint synoviocytes and human keratinocytes. And these currents are clearly inhibited by knocking down of PIEZO1 gene shown here. So x-axis shows that pressure application, and that y-axis shows the size of current activated by pressure. So when we apply large pressure, these channels are activated. So red shows that this point, blue shows this point. So these currents are clearly inhibited by knocking down of PIEZO1. So I show you that a comparison of a PIEZO1 current between human and chicken. So when we applied Yoda to PIEZO1 in human and chicken in a whole cell configuration mode, you can get a clear increase of outward current and inward current, plus 90 and minus 90 millivolt. As you can see, this patency by Yoda is relatively larger in chicken. And again, I applied pressure to human PIEZO1 and chicken PIEZO1. Again, this current shows chicken PIEZO1 current is relatively larger than human. Very clear pressure dependent current induced. This is a summary of this data. So this axis is quite larger than this one. So here I showed you the response of human piezo and chicken piezo to Yoda gain and gadolinium. As you can see, when we applied 20 millimeter Hg pressure, to human piezo, we can get some pressure like current. This current is increased by application of iode, and this current response are blocked by gadolinium. So quite similar when we apply iode and gadolinium. So chicken PIEZO1 is also again increased by iode and inhibited by gadolinium. So I showed you that outside the patch data again, current are activated by pressure at minus 60 millivolt as a holding potential, and at plus 20 millivolt. So as you can see, when we applied pressure to human PIEZO1 and the chicken PIEZO1, again we can get the current dependent on the change of that pressure. So pressure-induced current is relatively larger in chicken than human. So here I showed you that response of chicken PIEZO1 to lower concentration of iode at 0.1 micromole. As you can see, when we applied 0.11 micromole iode to chicken piezo, clearly current are potentiated, and this potentiation was reversed by the removal of iode 1 at 0.1 micromole. So this is a final slide of PIEZO1 result. Here I showed you that a part of comparison of amino acid sequence between human and chicken. Roughly speaking, transduction module and pore module are well conserved between human and chicken. However, in central proud region, the identity is around 30%. In addition, 5 amino acids which produce gain of function mutant in human are replaced in chicken. So this kind of change in central plug, or this amino acid change will change that size of current that responds to iode. So this is the collaborators. Thank you for your attention.
Question up the back.
Damien Bell. Lovely studies, Professor Muraki. I don't know the PIEZO1 channel too well, but I was interested whether there's any specific distortion sensitivity to the PIEZO1. So it looks like you had inside-out patches and you were applying a positive pressure, which would presumably mean it would be a convex surface applied to your inside-out patch. Have you ever tried, for instance, or other people in the field ever tried negative pressures or inside-out versus outside-out pressure, outside-out patches?
Thank you for your question. In this case, I applied the pressure to exercise outside the patch, not inside a patch. So in our limitation of apparatus by which we can apply pressure, we can just only apply positive pressure in outside the patch mode. We never try to apply other type of pressure inside out patch or cell attached patch.
Thank you.
Okay, if there's no more burning questions, then I would like to thank you very much for a fantastic presentation.